All right, so this next section, like I said, it's going to be very math intensive. But to start out, we're just going to kind of introduce. You're going to see some delta H's right off the bat. Don't freak out. Oh my God, there's equal signs adding everything together. Oh boy, we got a negative, you know. Okay, hold on. So just let's buckle up. This is going to begin the math. The next video I do is going to be much more math intensive. This is just kind of introduce the pieces. You know, introduce the cast, if you will. Let us know who the players are here. So what we're going to talk about is dissolving ionic compounds in something like water, dissolving them into a solution. And we've talked about what this is physically, like what's happening with this process. Well, the dipole-dipole interactions are pulling the ionic compound apart by getting in the way of those ion-ion interactions. And we've talked about it physically in kind of like hand wavy and just sort of general overview. Now we're going to talk about it mathematically. So we're going to actually bring some numbers into play here. We're going to talk about energy and enthalpy changes associated with these processes. And so what we have is a delta H solution. It's kind of like our overall change in enthalpy, which we can use as a stand-in for energy as well. That's the change that happens from dissolving something. And so if this is negative, it's going to dissolve. If it's positive, probably not going to happen. Or maybe it does. Yeah, there's some other driving forces, but right now we're just going to look at delta H. Yeah, so it could be positive or negative and happen, but it's going to happen easier if it's negative. All right. So we've got three pieces, and we've talked about what these are, but let's describe them. So we've got a change in enthalpy associated with pulling the ions apart. Okay, that's the first thing we got to do. We got to separate those ions. So there's going to be an enthalpy change from that. There's also going to be an enthalpy change from getting in the way of the dipole-dipole interactions. So the solvent molecules are interacting with each other, and then an ion gets in the way. So it's going to break up those dipole-dipole interactions, and what subs in their place? Ion-dipole interactions. That's what we're going to be looking at. So all together, we've got to break the ion apart. We've got to make room in the solvent, and then an ion comes into play. And so this needs to be very favorable for the process to occur favorably, because this is going to be a positive value. Pushing things apart is not favorable. This is going to be a positive value. Pulling ions apart is very unfavorable. But this could be favorable or unfavorable, it just depends on the situation. But it needs to be favorable enough that it will drive the process. And what does that mean? Well, we'll talk about it. All right, so the first thing is we're actually going to take this three-piece equation and we're going to break it into two pieces. And so we can also say delta H solution is equal to negative U plus delta H hydration. So fun with notation, right? And so that'll be the form that you generally see. You're not going to see this three-piece formula very much. And so U is related to the ion-ion interaction. And so delta H ion-ion is actually equal to negative U. And U is the lattice energy. And so what it is it's the stacking energy of that ionic compound. And so if we're going to tear an ionic compound apart, well, the energy or the enthalpy associated with that is going to be the negative of the energy used to stack it together. There's a certain amount of energy released when the ionic compound comes together. You got to put that back in to tear it apart. So it's just, conservation of energy in play. And we use U because, I don't know, all the other letters were taken. All right? I don't know why we went with U. It gets used as a stand-in for energy a lot in older notation. Now, usually you see capital E. But anyway, in this chapter, U equals lattice energy. And, like I said here, so if 1 mole of ionic compound is forming from the gas phase, so you have like gaseous Na+, gaseous Cl-, they come together to make NaCl, that would give you the lattice energy. You do that with 1 mole, or to make 1 mole of NaCl, you get the lattice energy. So it's going to seem a little bit weird. It's kind of very theoretical because we're not usually making ionic compounds out of gases. So just hang in there. It's just to make the paperwork push through at the end of the day. That's what we're doing. And, it's equal to, Q1 times Q2 divided by D times the K constant. So I've replaced my proportional sign with an equal, and then I sub in this constant, and you'll learn more about that in the next chapter. But we can bring in that equal sign. And again, it's just as the charges increase of our ions, U is going to increase. We're going to have more attractive forces between those ions. As they get closer together, D gets smaller distance between the ions. Our attractive force becomes stronger. We have more lattice energy. There's more energy stored in the lattice. All right. The other piece of this equation, delta H hydration. So this is the change in energy associated with just the ionic stuff. This is the change in energy of the solution, okay? And it's just, well, the energy associated with dissolving gas phase ions. So essentially, this is like we take our solid ionic compound, we tear it into pieces, we put it in the gas phase. That's the energy here. And over here, we dissolve those pieces in solvent. Might be water or whatever. And all together, that gives us delta H solution. And so we can measure delta H solution. In fact, if you took 221 here at Lane, you have. We did the calorimetry lab. You had your, we don't have coffee cups anymore. We had the really fancy new styrofoam calorimeters. And you dissolved ammonium chloride, NH4Cl, in water. And then you might have been freaked out because the solution got colder, and that meant that delta H solution was a, would that be positive or negative? Well, it was an endothermic process, so it was positive. Or was it negative? No, it was positive because it was taking heat from the surroundings, right? Good old fun with negatives, right? Plus or minus. Well, that'll be back a little bit of weaponized positive negative, but hang in there. So we had a positive change. The heat energy was absorbed by our reaction. So it gained energy. The solution, the surroundings, I should say, was where that energy was pulled from. So they got colder. So our thermometer registered a colder temperature because we had a colder solution. And so delta H solution can be positive or negative, as you saw in 221. And when we look at our lattice energy U, there's two things you can do. You can look them up in table 11.2, which is on page 543. Or, and this is what the next video will be about, we can calculate them using the Born-Haber cycle, which is kind of like a Hess's law remix. We'll talk about it. It's like Hess's law in a very specific situation. And you know, Born and Haber figured it out together, so they got their name on it. I'd be mad if I was Hess. I'd be like, hey, you just took my thing and like, you know, a little niche version, all right? Should be the Hess's Born-Haber cycle or something. All right, or Born-Haber Hess's law, you know. I would stake my claim. All right, and then the last thing is, we can figure out what delta H hydration is if we know what delta H solution is by measuring it with a calorimeter, for example, or you know, looking it up or estimating it some other way. We can look up or calculate our lattice energy, and then we can figure out what delta H hydration is through the cunning art of, well, I guess it's actually addition because we'd add U to both sides. So delta H hydration will equal delta H solution plus U, and that'll be like the last video we do in this section, just to remind you about that. And so those are going to be how we apply these equations. And so first, we are going to focus on this guy right here in the next video. Well, I guess it's second, right? This was the first video. But next, there we go, that's the word. We'll focus on using the Born-Haber cycle to calculate U. All right, so the next video will be more math intense. Right now we're just kind of like diagramming equations. Now we're going to put some stuff into play. A little bit of it, if it starts to look familiar a little bit, like I said, it'll be Hess's law, and I'll try to make that clear at the end.